Traditional scientific disciplines have adopted machine learning models at a rapid rate, from mapping the spread of civil conflict to predicting medical diagnoses. Algorithms are now embedded across the quantitative sciences. Researchers are routinely abandoning established statistical methods in favor of newer, complex algorithms. The justification is almost always the same. These new models appear to significantly reduce prediction error compared to established baselines. This chart plots the findings of a comprehensive review by Princeton researchers Sayash Kapoor and Arvind Narayanan. It maps 329 peer-reviewed papers spread across 17 distinct scientific fields that suffer from catastrophic reproducibility failures. The common thread across these failures is a single, subtle flaw hidden in the data preparation process: data leakage. The peer review process across all 17 of these disciplines is missing a textbook machine learning error. As a result, entire fields are correctly constructing their research on statistical quicksand. To understand exactly how this happens, we can look at a specific, high-stakes case study: the prediction of civil war. Recently, top political science journals published several papers claiming that complex algorithms, specifically random forests, significantly outperform decades-old logistic regression baselines when forecasting conflict. This chart compares the reported area under the curve, or AUC scores. The random forest performance towers over the traditional baseline. But when Kapoor and Narayanan corrected the math to prevent data leakage, the complex model's performance dropped to match the traditional baselines exactly. In commercial engineering, developers use blind third-party holdout sets or limited production deployments to catch these errors. Academic science rarely employs those defensive measures, leaving researchers vulnerable. The claimed breakthrough in Civil War prediction was an illusion. The complex models performed no better than basic baselines because they were simply exploiting a hidden error in the data pipeline. The root cause of this error stems from a clash between two different ways of doing science. In traditional explanatory modeling, the goal is to understand relationships, so researchers draw inferences from a complete dataset. In this explanatory flowchart on the left, missing data triggers an imputation process across the unified data block before analysis. But predictive modeling prioritizes out-of-sample validity by splitting data into a distinct training set and testing set. The error occurs when researchers apply their explanatory imputation habit to the predictive pipeline, placing imputation before the train-test split. By filling in the blanks before dividing the data, the imputation algorithm gets to peek at the target variables in the test set. Information from the testing data bleeds into the training data. Copying traditional statistical preparation into modern machine learning pipelines compromises out-of-sample validity. In the audited Civil War study, researchers used a random forest imputation algorithm to guess the missing values in their dataset. To see the mechanical impact of this choice, we can isolate a single variable from their data: agricultural exports. This density plot shows the actual real-world distribution of agricultural exports. The two curves representing nations experiencing war and nations experiencing peace are wide, messy, and heavily overlap each other.
But the imputation model filled in the missing test data by looking at both the training data and the target labels in the test set. It locked on to strict correlations and ignored the natural noise of the real world. When we inject those newly imputed data points, the overlapping curves violently separate into two sharp, distinct peaks. The data has been artificially clustered. This clustering effect was extreme because the out-of-sample test set used in the study was missing 95% of its values. The imputation algorithm was overwriting almost the entire dataset. With a 95% missing data rate, the final random forest model was not predicting the chaotic social outcome of civil war. It was exclusively predicting the synthetic output of its own imputation algorithm. This explains exactly why the baseline models failed where the machine learning models succeeded. Monotonic algorithms like logistic regression evaluate variables constantly in one direction. Returning to the corrupted density plot, logistic regression must draw a straight, continuous boundary. It struggles to divide these irregular, sharp peaks. Ensemble models like random forests operate differently. They evaluate data using localized, non-linear boundaries, drawing precise, tight boxes around any isolated cluster. Because of its flexibility, the random forest algorithm easily memorized the unnatural clustering created by the faulty imputation step. That precise clustering only exists because the test data leaked into the training data during pre-processing. The superior performance of the random forest was an artifact of the pipeline. It succeeded due to its capacity to seamlessly memorize the researcher's own methodology errors. Joint imputation is just one subcategory of the data leakage problem identified in the literature review. There are multiple ways a predictive pipeline can break. There is temporal leakage, which occurs when researchers use standard k-fold cross-validation on time series data, effectively feeding future events into a model trying to predict the past. There are illegitimate features, where proxy variables that represent post-event outcomes are accidentally included in the model to predict pre-event statuses. These errors pass through peer review because academic journals lack a standardized diagnostic framework for evaluating predictive data pipelines. Data leakage represents a systemic failure of researchers to properly map their data pipelines to the physical flow of time and reality. To catch these errors before publication, researchers have proposed a structural solution, the model info sheet. The first mandatory section requires model creators to explicitly map how clean separation was maintained between training and test sets through every single pre-processing step. Second, researchers must logically justify why every feature is legitimate, proving the data is knowable at the time a real-world prediction is made. Third, they must prove the test set perfectly mirrors the true distribution of real-world scientific interest, verifying it represents the environment they claim to study. This forces the burden of proof to permanently shift from the peer reviewers back to the model creators themselves. But the ultimate requirement for trust in quantitative science goes further. It requires complete computational reproducibility. Until shipping exact code, complete data, and identical environment dependencies becomes the universal standard across academic journals, claims of machine learning breakthroughs in science must be